Does the feeling of standing at the bottom of a massive mountain, a huge, overwhelming obstacle in your path, seem a bit familiar?
It's just impossible. There's so much to learn.
I've got so many books to revise from. I just don't know where to start.
How do they expect us to cope?
I just feel like running away.
Your task seems so enormous, you can't see how you can overcome it. So how do you tackle it? One step at a time, by planning out your route and knowing what you'll be doing at every point on the way. Even if your goal isn't in sight, you know you're getting there. And a major part of that is organising your revision, which is where we come in.
First, we shall look at some of the basics in a range of topics. Then, use that to work through exam questions with an examiner. An examiner sees where most people go wrong. We want to know how to avoid those pitfalls, and it would also be a help to have some tips on exam technique.
Well, that's what we can do. What we can't do is teach you the whole syllabus. We can't even give you a crash revision course. But if you use this program properly, you should have a good idea of what the examiner expects you to know and the best way to present it to get the most marks you can. Here is our physics examiner, Di Barton.
Hello.
Di, what qualifies you to assess all these students?
Well, I teach physics in a comprehensive school and I work with students every day, so I have a pretty good idea of what they can do.
What's the point of the physics exam?
Well, I'm simply trying to find out what the students know. I don't set questions to catch them out. I just want to give them opportunities to show what they've learned.
What do you have trouble with in physics?
It's the words that muddle me. Speed, velocity, acceleration. I thought they were the same.
I learn the formula, but I never know when to use each one.
There's always too much information in the questions.
It's just like maths, all numbers and symbols.
I don't see how a graph can tell you what a real car is doing.
Okay, so here's our examiner. Now is your chance to ask her anything that may be troubling you.
It's the words, just the way everything's written down, that I find confusing.
Well, physics has its own language, just like most subjects, but you only have to learn the meaning of a few words.
Well, come on, Dad, there must be more to it than that.
Well, you use a few simple ideas from maths, but basically it's common sense.
Well, let's just have a look at the first topic and see how much of it is just common sense.
The distance from A to C depends on the route taken. You could travel a long way from A to B to C, or go directly from A to C. Both routes would give you the distance from A to C, but it depends on which you choose. The displacement of C from A is the distance as the crow flies, and does not depend on the route. Speed is calculated by distance divided by time, and average speed is the total distance divided by the total time. Velocity is calculated by displacement divided by time. Both distance and speed are scalar quantities, and displacement and velocity are vector quantities. In other words, they have a quantity and a direction.
Now, let's look at a problem, and Di, could you talk us through it and show us how you would mark it?
A man has a bet where he runs a race against a greyhound. This graph shows how they moved during the race.
Any volunteers? Oh, Martin, thank you very much indeed. Thank you. Right. The first part, what was the distance of the race?
200 metres.
Yes, but how did you get that answer?
Well, that's as far as either of them went according to the graph.
After how many seconds did the dog overtake the man?
It looks like 11 seconds.
You should use a ruler to check it exactly. It could be 10.8 or 11.2.
I'll make it 11 seconds exactly.
Part 2. How far from the start did the dog overtake the man?
That's 80 metres.
Calculate the average speed of the man.
Average speed, that's distance divided by time, so that's 200 metres in 25 seconds. So that's 200 divided by 25, which is 8.
And you must add the units as well.
Metres per second?
Right.
After 8 seconds, was the man's speed increasing, decreasing, or staying the same?
Well, at that point the graph was straight, so he must have been staying the same.
Yes.
What's the speed of the dog after 18 seconds?
Well, speed is distance divided by time, so...
Slow down, take a look at the graph.
Well, the dog had finished at that point, so he was travelling at 0 metres per second.
That's right.
But come on, Di, come on. That is sneaky. Putting a question in about the speed of the dog after it had finished the race. Now, that's a trick question.
It's not really a trick question. Physics is about the real world and observing it, and that's where common sense comes in.
Well, it's all very well having these grand ideas about observing the real world, as you put it, but what does that mean to somebody who's actually sitting the exam?
Well, the answers in the exam have got to be realistic. If, for example, you came up with an answer which said a man ran a 100-metre race in 2.5 seconds, that would be some world record. Quite unrealistic and probably the wrong answer.
What else bothers you?
Well, I'm not sure about the differences between balanced and unbalanced forces.
Right, well, let's have a look at some background before we go on to another question.
For a car to maintain a constant velocity, all the forces acting on it must be balanced. The force from the engine must balance the tyre friction and air resistance, so there is no overall force. The forces are balanced. If the force from the engine is greater, you would accelerate. If the friction forces are greater, you would decelerate. The forces are unbalanced. Acceleration is measured as the change in velocity divided by time. Newton recognized that the amount of unbalanced or resultant force was responsible for changing velocity in a mass. The force needed is the mass times the acceleration.
Here's a question on that.
A rider and his moped have a combined mass of 85 kilograms. The average acceleration from rest is 0.6 meters per second per second. Calculate the average unbalanced force acting on rider and moped.
Right, go for it.
I'll use the formula. Force equals mass times acceleration. So force is 85 times 0.6. That works out to 51 newtons.
On we go.
Eventually, the moped reaches the top speed, so that although the engine is still applying a force, the moped and rider do not accelerate. Draw a diagram showing the horizontal forces acting on the moped and rider at the top speed.
Kerry, you've already done that, so let's see it. All right, explain what's what.
The block represents the rider and moped, and the motor is giving a force of 51 newtons.
But the question said the bike is at top speed and can go no faster. Well, you've given it an unbalanced force which would cause it to accelerate.
It must be balanced by 51 newtons of friction the other way.
That's right.
Di, graphs seem to be involved in this topic. Is it the same as dealing with them in maths?
Graphs in physics are not quite the same. Graphs are drawn from experimental results and then used to see if a pattern exists.
So what difference does that make in the exam?
Well, you don't just join up all the dots and produce a jagged line. You try and draw the line of best fit. That's a curve which goes through all the values.
Right.
Don't expect it to be nice and neat every time.
Now, Di, calculators are allowed in the exam, are they?
Yes, they are.
Can they cause any problems?
Yes, they can. It's easy to assume the answer the calculator gives is accurate when a simple slip-up or misreading can give you the wrong answer. You have to use your common sense to see that your answer is sensible.
Now, a calculator can give you a very long answer. Is that what you're looking for?
No, I want sensible numbers. For example, it's not practical to measure the speed of a car to 5 or 6 decimal places.
What do you want in the exam?
The number of decimal places in the answer should not be more than the least number in the question. For example, if you had the numbers 11.5 and 2.25, the answer would have to be to 1 decimal place, like the 11.5. That's especially important when you're using pi, because it gives you a very long calculator answer.
I think it's really hard to understand. I mean, you can't see electricity.
Circuit diagrams, I don't understand them.
I just get really muddled with the amps, volts and watts and all those other figures. You can't see what's going on inside the wires.
Now, circuits and direct currents. What do you want to know?
What does go on inside the wires?
Quite a lot of people don't understand how electricity works and find the terms confusing.
So let's do some revision.
Conductors of electricity contain charge carriers which are part of their atoms. They can flow through the material if they're given energy from a battery or power supply. A coulomb is the name given to 6.2 times 10 to the 18 of these charge carriers. If an ammeter registers a current of 1 amp, it means that 1 coulomb of charge carriers is flowing every second. At the battery in a circuit, the charge carriers acquire energy from the chemical energy in the battery. A voltmeter registering a voltage of 1 volt means 1 coulomb has 1 joule of electrical energy that can be converted into another form of energy, such as heat, light, or kinetic energy.
This looks quite daunting. It's a very long question, Di.
Well, it's made up of short parts to make it easy to progress from one stage to the next. The parts get harder, but everyone should be able to do some, so just take it bit by bit.
Let's tackle it.
This diagram shows the inside of a mains-operated hairdryer. The fan can blow either hot or cold air. The diagram below is a circuit diagram of the same dryer, showing how it is wired up for use.
Natalie, which switches need to be on to get the machine to blow hot air?
A needs to be on for the heater to work, C needs to be on for the motor, and to get it all to work, B has to be on.
That's right.
And which switches are needed to get cold air?
We don't need the heater, so it's just B and C.
That's fine. Well done.
Part B. Explain carefully what would happen if the heater was on and the fan failed.
It would explode.
That's probably true, but the question asks you to explain carefully, so you'd need to say more than that to get all the marks.
Well, with no fan, there's no airflow, so the heater would overheat and the wires would get very hot. I suppose the casing would melt or even catch fire.
Yes, that's the sort of nice, clear answer I'd be looking for.
I didn't think hairdryers were part of the syllabus. Why did you put a question in like that?
You'll always find some questions which test your ability to apply your knowledge in a new situation. It might not be something you recognise, but you should have enough knowledge to be able to tackle it.
Right.
The secret is don't panic, stay calm and think it through.
We haven't finished the hairdryer question yet, but before we do, is there anything else you want to know about?
I'm not sure about resistance and power.
Watch this.
Resistance is the property of materials which controls the flow of a current. It is measured in ohms. 1 ohm means that 1 volt is needed to drive 1 amp through a circuit. For many materials, the current and the voltage are proportional. This is often written as voltage equals current times resistance and is known as Ohm's law. Power is the rate at which energy is converted. 1 watt is 1 joule of energy per second. Power is calculated by multiplying voltage and current.
We're carrying on with the marathon question about the hairdryer. The details of the fan are 250 volts and 500 watts. Calculate the current from the supply when the dryer is working at its full stated power.
We'd have to use the formula. Power is amps times volts. So current is power divided by volts, which is 500 divided by 250. That's 2 amps.
That's right.
Fuses for the mains of 3 amps, 5 amps and 13 amps are available. Which fuse would you choose for use in a plug attached to the dryer, and which wire in the mains cable would you connect to the fuse?
I'd use a 3 amp fuse and connect it to the live side.
Wouldn't a 5 amp fuse work?
Yes, but the current could rise above the safe working value. So 3 amp fuse is the answer I'm looking for.
Right, on with the question. Somebody needs to use the dryer for 10 minutes. Calculate the energy converted during this time.
Energy, that's power times time. So it's 500 watts times 10 minutes, which is 5,000 joules.
Now be careful, power in watts is the energy converted in 1 second.
Oh yeah, 10 minutes is 600 seconds. So it should be 300,000 joules.
That's right now. Always think to yourself, before you put the numbers into the formula, have you got the correct units?
Di, answering this hairdryer question has required a lot of formulae. Are students expected to know them all?
Well, some exam boards do give you the formulae and others expect you to learn them.
So what are you meant to do? Know what your particular exam board does?
Well, it could help everyone to learn some of the formulae, but it's more important to know how to use them.
Di, how much detail are you actually looking for in an exam answer?
I need to see how an answer is reached. If you use an equation, I want to know which one it is and how the values are substituted and how the final answer is reached.
Why is that?
If I don't see the working out, I can't give any marks for it, especially if the final answer is wrong and that's all there is.
So an ideal exam answer would actually show every stage of the working out?
Yes, and the correct units, and that's especially important with electricity. You should always check you have the right units.
Well, I can see everything's made up of particles, but I'm useless at explaining it.
I'm always being told I don't put enough details into my answers.
I don't know the difference between specific and latent heat.
I can't do calculations about heat.
What do you all want to know about this then?
Well, in chemistry, we talk about atoms, molecules and ions. Why is it different in physics?
It's much the same in physics, but in kinetic theory we simply refer to everything as particles to make it easier to describe differences in behaviour between solids, liquids and gases.
Well, here's some background information on that.
Solids have strong forces of attraction and repulsion between the particles. This gives them rigidity and makes them hard to compress. Liquids have forces which are slightly weaker between particles. This allows liquids to flow. In gases, there are virtually no forces between particles because the particles are so far apart. The hotter a gas becomes, the greater the internal energy of its particles and the faster they travel. So particles will collide with a container harder and more often, causing an increase in pressure or volume. If the volume is fixed, the pressure will increase, and if the pressure is fixed, the volume increases. This can be shown by experiment, and the graph of the result extended to show that at absolute zero, particles have no kinetic energy, are at rest, and exert no pressure.
Here is a question.
Assuming air is made up of molecules which are always moving, how do we explain why the pressure of the air increases as its volume decreases?
Di, that sounds like it's asking for some pretty complicated theory.
I'm only trying to find out whether you can apply particle ideas clearly. It's fairly straightforward.
If the volume changes, there's less space for moving particles. I can see that means an increase in pressure, but I'm not really sure how to put that into words.
Well, just take it a step at a time.
It's collisions that cause pressure, so if there's less space, the particles will move shorter distances before they collide with the wall, and the pressure rises because there are more collisions.
Yes, the only thing I'd rather you had said is more collisions in the same time, or more collisions per second.
How would you increase the pressure of air in a sealed container without changing its volume?
By raising the temperature.
Yes, that's all that's needed.
Explain your answer in terms of the motion of molecules.
In simple stages, volume is the same, but the temperature rises. Particles get more energy, so they move faster, so they hit the container walls more often. And more collisions per second means the pressure rises.
Yes, an excellent answer. Well done.
Now, we know that people have difficulties, but what are the specific problems that students have when it comes to tackling the problem of kinetic theory?
Well, they need to understand that when a state of matter changes, you can see an external effect, but the particles themselves stay the same.
So what has changed?
Well, the particles can either be rearranged, or because they have more energy, they're moving around more quickly and they're further apart. Many students think incorrectly that the particles themselves expand or get bigger.
But they don't. Okay.
I don't understand why you can keep heating water or something and its temperature doesn't always keep going up.
The temperature stays the same when there's a change of state from solid to liquid or liquid to gas.
Well, I think that needs some explanation.
A block of ice is taken from a freezer at minus 20 degrees Celsius and heated gently until it boils. While the block is below 0 degrees Celsius, the heat raises the temperature. The particles vibrate more rapidly as they gain energy. At 0 degrees Celsius, the temperature stops rising. Instead, the energy is being used to break the bonds that hold the particles in a solid state. Once the bonds are broken and the ice is turned to water, the temperature rises again. The amount of energy applied to cause a change of state without causing a change in temperature is called the latent heat. The heat energy required to raise the temperature of 1 kilogram of the material by 1 degree Celsius is called the specific heat capacity.
Okay.
A man uses the steam wallpaper stripper, shown here, to help him prepare his living room for redecoration. When the appliance is used, water is heated until it boils and produces steam. The plate is then held against the wall, and the steam released from the pipe slackens the paper. The information shown on the appliance is power rating 2.5 kilowatts, voltage 240 volts, capacity 20 litres. Tap water at 20 degrees Celsius is used to fill the tank. 1 litre of water has a mass of 1 kilogram.
Well, this is very different, Di.
Yes, this one needs calculations rather than the explanations of the previous question.
Right, the first part. What mass of water fills the container, Jacob?
Well, the container has 20 litres of water, and 1 litre of water has a mass of 1 kilogram, so it's 20 kilograms.
Yes, that's easy enough. All the information you need is in the question.
Right, calculate how much energy must be absorbed by the water to raise it to boiling point.
This is about specific heat capacity. I'm not sure what to do with this.
Well, you've identified the piece of information that you need in the question. Now, think about what it means to say that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin.
It means that it takes 4,200 joules for each kilogram to rise by 1 Kelvin. It's got to rise to 100 degrees Celsius to boil. The energy needed is 4,200 times 20 kilograms times 100 degrees.
But be careful, the water started at 20 degrees, so it only rises by 80 degrees.
So it's 6,720,000 joules.
Moving on, calculate the time taken for the water to begin to boil.
I'd need the power rating, that's 2.5 kilowatts. 2.5 kilowatts is the same as 2,500 watts, which is the same as 2,500 joules per second. I've got to get 6,720,000 joules, so it's 672,000 joules divided by 2,500, which is 2,688, or 44.8 minutes.
That's right.
And the last part. State whether, in practice, it takes a longer or shorter time to raise the water to boiling point, and explain why.
I think it'll take longer, because the container will heat up, and so will the air around it, so not all the energy goes into the water.
Yes, good. Overall, that was quite a successful attempt, and even if you had let some of those errors slip in, the method was quite clear. That's where most of the marks are.
Di, that was a pretty long and involved question.
Yes, it was fairly testing, but there's no need to panic. The information's in the question, but it's not always that obvious.
What do you mean by that?
The units in the data are also carrying information. The 4,200 joules per kilogram per Kelvin tell you that 4,200 joules of energy are needed to heat each kilogram by 1 degree.
So there is some help there as long as you can spot it.
Yes, and that's where you need to revise so that you know what the question is telling you.
Di, not all the questions in the exam are about number crunching. Some actually involve describing things. So how long an answer do you want? An essay every time?
The best way is to look at the number of marks available for each sub-question. If there's 1 mark available, then 1 word or 1 sentence answer is enough. If there are 3 marks available, you'll need to write 3 statements to get full marks.
So you do want an essay every time?
Not necessarily. Don't forget that a diagram can contain quite a lot of information, and it's often clearer in a diagram than writing it out.
Amplitude, frequency, period, wavelength, and I get muddled. I never know what units to use.
Diffraction, interference.
There's so many different sorts of waves. Radio waves, ultraviolet waves, C waves.
Now, more problems.
I still get confused with the words like frequency, oscillation and period.
Well, that's just a matter of learning the language of physics. If you put some effort into learning the words and what they mean, you'll find understanding the physics much easier.
Here's some revision on the words.
This diagram represents a wave. From point X to point Y is one complete cycle of the wave. The frequency in hertz is the number of cycles per second. The velocity of a wave is calculated by multiplying frequency in hertz by wavelength in meters. The velocity of a wave is measured in meters per second. A sound wave of a pure note shown on an oscilloscope would look something like this. If the sound were louder, the amplitude of the wave would increase, and if the pitch of the note went up, the frequency would increase.
All electromagnetic waves travel at a speed of 300,000 kilometers per second in vacuum or in air. What is the time taken for a radio signal to travel from Britain to New Zealand? 18,000 kilometers.
Let's see you try this, Miranda.
This is a velocity question. So it's velocity equals distance divided by time. Check the units, all in kilometres. That works out to be 0.06 seconds.
That's quite correct.
I thought velocity for waves was frequency times wavelength.
Well, if you think about it, frequency is the inverse of time. So many cycles per second instead of so many seconds per cycle. It's just the same as distance over time. It was just disguised a little.
Okay, how long does it take for a radio message to travel from Earth to an astronaut on the moon? That's 320,000 kilometres.
This is the same, isn't it? Only the formula's been switched round. So that's time equals distance divided by velocity. That's 320,000 divided by 300,000 equals 1.06 seconds.
Right again. You see, physics is easy as long as you're sensible and don't panic.
What's the most common mistake you find when you're marking wave questions, Di?
I think the most common mistake is identifying amplitude.
Right, sort us out then. What should it be?
When a wave passes through a material, the particles oscillate. The amplitude is the maximum displacement from rest, not the total displacement.
Could we have another suggestion?
Reflection, refraction, interference and diffraction. We haven't done anything about those yet.
Well, interference and diffraction are important because they are unique to waves.
Well, I think we should have a look at them.
All waves can be reflected. For example, the reflection of a sound wave is an echo. Waves can change velocity when moving from one material to another or one region to another. If the wave approaches the new material at an angle, the change of velocity can also give a change in direction. This is called refraction. The properties of interference and diffraction are unique to waves. When waves overlap, they combine to give an increased or decreased amplitude. If the two waves had originally the same amplitude, frequency, and wavelength, a constructive interference would double the amplitude, and a destructive interference would result in a cancellation. Diffraction happens when waves pass through a hole in a barrier. They spread out beyond the edges of the barrier.
Two loudspeakers in a large open space were connected to the same audio frequency generator, as shown in this diagram. A person walking from A to B in front of the loudspeakers found that the sound level varied in a regular pattern.
Okay, the first part of the question, Natalie. What name is given to the effect causing this variation in sound level?
That's interference between the two sets of sound waves.
That's right.
Now, explain using a labelled diagram how this effect occurs. And let's have a look at the one you've already drawn. Explain it using that.
Well, this shows the sound waves arriving at two different points. At the top, they arrive in phase and they reinforce, making it sound louder. At the bottom, they arrive out of phase, cancel each other out and make it sound quieter. It just depends on how they mix.
Well, that's not quite how I put it. Waves can superimpose, and the effect is the result of two or more amplitudes combining.
But how would you have marked that? Because surely you knew what she meant.
Yes, well, we tried to read between the lines, and a lot of credit would be given for good, clear diagrams, although probably not full marks.
On to the next part, the last part. Suggest two reasons why a domestic stereo system does not usually show such regular changes in sound level.
That's because it gets evened out by echoes from the walls and ceilings in the room. I can't think of another reason.
Well, the other answer I'd look for is that a stereo operates over a wide range of frequencies, so you wouldn't get the same interference pattern as for a single frequency.
I must admit, Di, I thought you were a bit hard on that last question, the way the answer was put.
Well, physics has its own very precise vocabulary which should be used.
Yeah, but what does it matter if you know what's meant?
Well, using everyday expressions doesn't tell the examiner that you understand the physics. There's quite a difference between saying waves blanking each other out and the term destructive interference.
Di, some of these questions are very long, and that's enough to confuse people without going into the physics. So how should these questions be tackled?
People shouldn't be put off. It may seem very obvious, but you should always read the question very carefully, and then you can sort out the information by underlining the key parts of the question.
You can't expect everyone to do all parts of the question.
No, in the structured questions, everyone should be able to do some parts of the question. The secret is to do the bits you can do and leave out the parts you can't do.
Direct currents are okay, but how can a current going backwards and forwards do anything? Transformers. What's a transformer?
The questions never seem familiar. I mean, we've done a lot of experiments, but in the exam, the questions seem to use different apparatus.
I don't know about all of you, but I don't know what induced EMF means.
EMF stands for electromotive force. If you think back to direct currents, the conversion of chemical energy in a battery to electrical energy creates a voltage or electromotive force. Induction is about producing electrical energy from kinetic energy using magnetic fields.
Well, I think that definitely needs some more explanation.
A single wire connected to a sensitive galvanometer and moved in a magnetic field causes a movement on the galvanometer showing that a small current flows. The flow occurs only when the wire moves and only when it cuts through a field. Electromotive force, or EMF, is induced by a change in the field around the wire, and a current flows if the circuit is complete. This change could be moving the wire, moving the magnetic field, or increasing the magnetic field. To make the EMF larger, the wire is wound into a coil and stronger magnets are used, giving a bigger effect. EMF is only available for a short time, so to give a continuous EMF, you need to make continuous changes to the field around the coil. In a dynamo, a coil rotates in a field, so the field around each arm of the coil is changing all the time, giving an alternating current.
What's this question about?
Well, it's about EMFs.
Let's have a look at it.
A man makes an anemometer, a device for measuring wind speed, out of the apparatus shown, and positions it on the roof of his garage. When the wind blows, the spindle rotates, and the AC voltmeter pointer is deflected to give a reading.
So now, let's look at the first part of the question. Explain how the rotating spindle causes the voltmeter pointer to be deflected, Andy.
It's nothing like any of the apparatus I've seen before.
If you look at it, it's only a magnet and a coil, and you should know about that, even if you don't know about anemometers.
As the spindle rotates, so does the magnet and its magnetic field. The magnetic field linking the coil is continuously changing because of the iron core, like a bicycle dynamo. That means there's an induced EMF, but it changes size and direction continuously depending on how the magnetic poles are moving.
Yes, and that's why you need an AC voltmeter.
Part B, when the wind speed increases, what difference, if any, would you expect in the voltmeter reading, and why?
Well, if the wind speed increases, the magnet turns more often, the field changes more rapidly, so the reading's bigger.
Now, the last part, Andy. Give 2 ways in which the apparatus could be modified so as to obtain a larger reading on the same voltmeter.
I suppose a stronger magnet and more turns of wire in the coil will both give bigger readings.
Yes, well done. You sorted out the ideas once you realised which parts of the apparatus to look at.
It still seems a bit confusing to me. EMF's always there, even when nothing's happening.
Well, think of a torch battery.
Right.
The EMF is always there, but the current can only flow when there's a complete circuit.
Mm-hmm.
In the same way, the EMF is induced when there's relative movement between a wire and a magnetic field, but the current's only induced when there's a complete circuit.
Transformers still sound pretty mysterious to me. I mean, a voltage goes in at one end and comes out different at the other.
We have an explanation.
Transformers use changing magnetic fields to step up or step down voltages. 2 coils, called primary and secondary, are wound on a central soft iron core. If an alternating EMF is applied to the primary coil, the alternating current causes an alternating magnetic flux in the core. The changing magnetic flux in the core then induces an alternating EMF in the secondary coil. The size of the secondary voltage depends on the ratio of the number of turns in the primary coil to turns in the secondary coil. If there are more secondary turns than primary turns, the voltage is stepped up. If there are fewer secondary turns, the voltage is stepped down.
And now, I presume, a question on transformers.
Yes.
A pupil is given 3 transformers, labelled A, B and C. She is asked to investigate the relationship between the primary, or input, and secondary, or output voltages of each transformer. She applies different voltages to the primary coil of each transformer and measures the voltage produced across the second coil. This graph was plotted from her results.
All right, Dave, now the first part of the question, and it certainly looks simple enough. Which transformer is operating as a step-up transformer?
A step-up transformer gives out a higher output than input voltage, and according to the graph, the only one that does this is transformer A.
Yes.
You'll have to look at this for the second part.
The primary coil of each transformer has 250 turns of wire. Complete this table using information from the graph where required.
For A, it's 7 volts primary, and on the graph it says 14 volts secondary. The step-up is 2 times, so it has to be twice as many secondary turns, which makes 500.
That's quite right.
B is 6 volts primary, and on the graph that's 5 volts secondary. I have to use the formula this time. Primary volts over secondary volts
equals primary turns over secondary turns. Substitute into that, and that means that the number of secondary turns is 5 times 250 divided by 6. I made that to be 208.3333, or 208 rounded down.
Fine, I can't fault that.
And for C, it's 4 volts secondary, and on the graph it says 8 volts primary. That's stepped down by a half, so the turns are half, 125.
Very good.
These transformer questions are pretty complex, Di, like the topic. What's the best way to get started on them?
Well, approach them in the same way that we did the questions on kinetic theory.
Right.
Break the explanation down into simple logical steps. Many students say something like the primary current causes a current in the secondary.
What should it be then?
There are a number of steps. The primary EMF to the current, to the field, to the secondary EMF.
Now, Di, one of the things you're always telling us is that physics is concerned with the real world, but I bet you the exam doesn't go much further than bicycle dynamos and anemometers.
No, most of the exam boards do include some aspects of social or economic implications of physics in the longer questions, so students do need to have some background ideas as well as the basic knowledge.
And where's that meant to come from?
Well, there's the textbook to start off with. Most of them include details about the applications of physics.
Pardon my cynicism, but I wouldn't have thought that textbooks were the best place to learn about the real world, Di.
No, there are other sources like newspaper and magazine articles, and then there's the radio and TV. The news and scientific programs should help you relate physics in the laboratory to its uses in everyday life.
I don't do chemistry, so I don't understand how atoms are made up.
What's really going on with forming ions?
Well, electrons, neutrons, protons, ions. There's so many to learn.
Half-life. Why only half?
Decaying atoms changing into new atoms.
I don't understand what radiation really is.
I think it would be best if we started with a simpler explanation of the structure of the atom.
Right, here it is.
An atom has a positively charged, very small nucleus surrounded by negatively charged electrons, which makes an atom electrically neutral. The nuclei of some atoms are unstable. They have excess energy, which they try to lose by shedding either high-energy particles or high-energy waves. These are known as alpha, beta, and gamma radiation. Alpha particles are made up of 2 protons and 2 neutrons, the same as a helium nucleus, and are positively charged. They cause a lot of ionization, but their energy is absorbed by passing through 10 centimeters of air, or a thin sheet of paper. Beta particles are high-energy electrons. They are less ionizing than alpha particles, but their energy is less easily absorbed. They can pass through a few millimeters of aluminium, but are absorbed by anything much thicker. Gamma radiation is made up of electromagnetic waves similar to X-rays, but more penetrating. It takes thick sheets of lead to reduce their energy. Unlike alpha and beta particles, they are unaffected by magnetic fields.
A Geiger-Müller tube with an automatic counter is used by a pupil to examine a radioactive source which emits one type of radiation only. When the Geiger-Müller tube is more than 10 centimeters from the source, an average count rate of 5 counts per minute is obtained. The Geiger-Müller tube is now moved until it is 2 centimeters from the source, and the results in the table are taken over a period of 80 minutes. The source is then removed.
Right, Martin, the first part of the question, what type of radiation is emitted from the source?
Well, there's so much information here. I don't know where to start.
As I said earlier, look at the question as a whole and try and get a feel for the data.
emits only one type of radiation, and at that distance of 10 centimetres away, the count is 5 per minute. So that level of background radiation is fixed, so it must be an alpha source.
I don't really follow that.
Because at more than 10 centimetres, alpha energy has been absorbed by ionisation.
Okay, moving on. Suggest what the count rate would be after the source is removed.
Well, the background radiation is always there at a count of about 5 per minute.
Now, plot a graph of count rate for the source against time and use it to estimate the half-life of the source. Now, you've already done that, so show us what you've done and also explain it.
I use the count rate per minute and time in minutes on the two axes, then plotted each of the points starting with 0 time and 101 count rate.
Unfortunately, that's where you went wrong. The 101 includes the background radiation, so on average there should be 5 less counts in a minute for the source. This is what your graph should have looked like. Now use it to try and estimate half-life.
Half-life is the time it takes for the activity to be reduced at any stage by half. 60 counts is easy to read on the graph, and it takes 30 minutes to reduce to 30, so the half-life must be 30.
It's always a good idea to double-check your estimates because radiation is a random process. From the first count, 96, down to half, 48, takes 30 minutes. That seems like quite a good estimate.
Finally, the pupil reported that the counter might be sticking since it appeared to be counting irregularly during the experiment. Now, comment on the pupil's interpretation of this irregular counting.
Like you said, it's a random process, so you're bound to expect some irregularity. But overall, the pattern's the same.
Di, in your experience as an examiner, what problems do you most often see students having with atomic structure?
I think it's the language again.
So what vocabulary needs to be learned?
Well, there are 3 main things. Atoms are electrically neutral.
Yeah.
Ions are just atoms which have lost or gained an electron. And protons, neutrons and electrons are all part of the atom.
Another suggestion, please.
I'm not sure how a substance can change into another one and be chemically identical.
You're referring to isotopes.
Shall we do some revision on that?
When a nucleus decays by emitting an alpha particle, it loses 4 mass units, 2 neutrons, and 2 positively charged protons. It changes into a new material, which can be shown as a nuclear equation. The upper number is the total number of protons and neutrons, and is known as the nucleon number. The lower number is the proton number, showing both the total number of protons and the charge. This is the general equation for alpha decay. In beta decay, a negative charge is lost, so the overall positive charge increases. Gamma decay does not affect the chemical nature of the material because it is only made up of energy.
Right. Which of these types of radiation does not travel at the same speed in a vacuum as visible light?
Alpha and beta are particles, so they wouldn't.
Yes.
Which are not emitted from the nucleus of an atom?
It's the radioactive ones that come from a nucleus, alpha, beta and gamma.
No, that's the sort of silly mistake that would cost you marks. The question said which are not emitted.
Oh, so it's the others, ultraviolet and infrared.
When radiation passes through matter, it may cause ionization. Now, explain briefly what is meant by ionization.
It's when an atom loses an electron and becomes an ion.
Nearly there. An atom can lose an electron and become a positive ion, or it can gain an electron and become a negative ion.
Now, this isotope of uranium decays with the emission of alpha particles to give an isotope of thorium. Name the particles which make up the nucleus of the uranium isotope, stating how many there are of each in the nucleus.
Protons and neutrons, 92 protons and 143 neutrons.
Yes, explain to everyone how you got those figures.
The bottom number is the number of protons in the nucleus, and the top number is the number of particles in the nucleus, so you take away the protons.
Excellent.
X represents the symbol of an element. Is this an isotope of uranium? And give a reason for your answer.
Yes, they both have the same number of protons, so are chemically identical.
Good answer.
Di, how are students to know what examiners actually want from them in the exam?
They need to look at the word of instruction at the beginning of each question. Words like state, describe, explain.
Right, it's quite obvious what they mean, isn't it?
Well, sometimes students write a description when they're asked for an explanation, whereas the word state means just one or two words are required. But wherever possible, try and use the correct scientific terms.
Well, Di, we've covered a fair bit of ground, but how can you actually go about the task of getting physics to stick in the mind?
I suggest students start revising in plenty of time, draw up a timetable and try and stick to it, and generally revise in an organised way.
Now, I know there's more than one type of course involving physics, so how does what we've actually done here fit in?
Everything we've talked about is relevant, no matter what type of science course you're doing.
And what's the best way to make use of a programme like this?
Well, watching it won't take the place of sustained revision. We haven't covered all of every topic in the syllabus. The topics we've talked about are the ones that the students suggested because they had problems with them. It would be best to watch the programme several times, or just the part that covers the topic that you're revising. Then you can go through the difficult bits over and over until you understand it.
I like the sound of that. You can rewind something the teacher says, or better still, use the pause button.
To help your revision, try the Longman G.C.S.E Physics or Science Revise Guide. It covers the whole syllabus with vital facts, examiners' comments to bring out key points, and lots of practice questions. Each chapter has worked examples to show how it should be done, and student answers to highlight common mistakes. Longman Revise Guides are written by examiners and are available for all major GCSE subjects.
Finally, I'd just like to wish you good luck in your exam. But then again, if you've prepared properly, what does luck have to do with it?